17.3 Simplifying Radical Expressions. The product rule for radicals states that the nth root of a times the nth root of b is equal to the nth root of a times b. So, in other words, if your radicals have the same index, and the index is this, if they have the same index, then you can just multiply the numbers or the expressions under the radical. In example 1, we will be applying the product rule. 1a is the square root of 5 times the square root of 13. So since they're both square roots, I can just multiply under the radical. So 5 times 13 is 65. So the square root of 5 times the square root of 13 is the square root of 65. b, the square root of 10y times the square root of 3k would be the square root of 10 times 3 is 30, and y times k is just yk. And it doesn't matter what order you put the variables in. Okay, example 2, we're still using the product rule. So a is the cubed root of 2 times the cubed root of 7. So since they're both cubed roots, the indexes match. My answer will also be a cubed root, and then I'll just multiply 2 times 7 is 14. Then for example b, the sixth root of 8r squared times the sixth root of 2r cubed is going to be the sixth root of 8 times 2 is 16. R squared times r cubed is r to the fifth, because remember you add the exponents. On C, the fifth root of 9y squared x times the fifth root of 8xy squared is going to give me the fifth root of 9 times 8 is 72. Y squared times y squared is y to the fourth, and x times x is x squared. And again, it doesn't matter which order you put the variables, so you could have also put the fifth root of 72 x squared y to the fourth, and that's also acceptable. D, the square root of 7 times the cubed root of 5. Well, since this index is understood to be a 2, and this is a 3, they don't match, then this one cannot be simplified using the product rule. The quotient rule for radicals states that the nth root of a divided by b is equal to the nth root of a divided by the nth root of b. So in other words, if your whole fraction is under the radical, you can break that up into the numerator and the denominator of the fraction, each being under a radical. So in example 3, we will be applying the quotient rule. So simplify, assume that all variables represent positive real numbers. A is the square root of 100 over 81. So the first thing I'm going to do is rewrite it as the square root of 100 over the square root of 81. And now notice that 100 is a perfect square, so the square root is 10. And the square root of 81 is 9. So we just take the square root of each and then simplify it if you can. 10 ninths can't be simplified any further. The b, I'm going to rewrite it as the square root of 11 over the square root of 25. So 11 is not a perfect square, so the square root of 11 can't be simplified any further. And then the square root of 25 is 5. On C, we're finding the cubed root, so this would be a good time to take out your list of perfect squares, perfect cubes, perfect fourths, so that you have that to refer to. So we're going to rewrite it as the cubed root of negative 125 over the cubed root of 216. Notice that I didn't put a negative on the top and the bottom. I just picked one of them. So the negative, you're either going to put it with the 125 or the 216, but not both. Alright, so the cubed root of negative 125 is negative 5, and the cubed root of 216 is 6. Alright, on D, the square root of y to the 8th over 16, so we'll rewrite it as the square root of y to the 8th over the square root of 16. Alright, so when you're taking the square root of variables, let's say I had the square root of x squared. Well, the square root of x squared is just x, right? Because x times x equals x squared. If I have the square root of x to the 4th, that's the same thing as x squared times x squared. So there's two sets of x squareds. If I have the square root of x to the 6th, I have x squared, x squared, x squared. So I have 3 sets of x squared. Okay, so you're basically taking, if I know that this index is understood to be a 2, so I can take 2 divided by 2, that's x to the 1st, 4 divided by 2 squared, 6 divided by 2 is 3. That's just kind of a shortcut. So in this case, in this case, this is a 2, so I'm going to have 4 sets of y squared in y to the 8th. So this is going to be y to the 4th. And that's the same thing as the 8 divided by 2 gave me the 4. And then the square root of 16 is 4. So this is y to the 4th over 4. And then E, if it's a cubed root, I need at least an x cubed for it to come out of a radical. So x squared is smaller than that. So it's going to be negative, we'll rewrite it, so cubed root of x squared over the cubed root of r to the 12th. Alright, so this would be 2 divided by 3, so it's not going to come out of the radical. So the numerator is going to stay cubed root of x squared. Now in the denominator, I have 12 divided by 3 is 4, so that's going to be r to the 4th. Okay, on this slide we're looking at the conditions for a simplified radical. So these 4 conditions will tell you that your radical is already in simplest form. If it doesn't meet all 4 requirements, then you need to take more steps to simplify it further. So the first one, the radicand, which is the number under the radical. The radicand has no factor raised to a power greater than or equal to the index. So for example, if this was 3 and this was x to the 5th, then that's not in simplest form. The exponent under the radical has to be less than the index. So I have one set of x cubed, like 3 goes into 5 one time, so this will come out once, and then there was 2 remainder, so x squared would be on the inside. So now my exponent in the radicand is less than my index, so this is in simplest form. Okay, our second condition is that the radicand has no fractions. So if it has a fraction, then you have to break it up like we did using the quotient rule, and then simplify. Step 3, no denominator has a radical. Okay, this is important. This is just a general rule for radicals. You never, never, never leave a radical in the denominator. If you have a radical in the denominator, I'm going to show you how to rationalize that. But your answer is not in simplest form. If you ever see a radical in the denominator, you have to take more steps. It's not simplified yet. And step 4, exponents in the radicand and the index of the radical have a greatest common factor of 1. So we can go back to this example, cubed root of x to the 5th. So 5 and 3 don't have any common factors other than 1. Now if I had 3x to the 9th, well, 3 and 9 both have common factors of 3. They're both divisible by 3. So I could simplify this, and that's actually just simplifies to x to the 3rd. Okay, in example 4, I'm going to show you how to simplify radicals. So the first thing you need to look for is the factors of the radicand, the number under the radical sign. And if it's a square root, like in examples A and B, you have to make sure that none of the factors are perfect squares. So again, it's a good idea, even though you know your perfect squares, it's a good idea to just be able to look at a list of it. So I'm just going to list my perfect squares here down at the bottom. So 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. Alright, so I'm looking at 32. Can 32 be divided by any of these numbers at the bottom? Yes, it can be divided by 4. So I'm going to break this up into, it can be divided by 4. It can also be divided by 16. If you take the greatest one that can be divided by, then there's less steps. So 16 times 2. Okay, so the square root of 16 is 4, and 2 is not a perfect square, and it's not divisible by anything from this list at the bottom. So the square root of 32 is equal to 4 times the square root of 2. Alright, for B, 45, the square root of 45. So the square root of 45 is divisible by 9. So this is going to be the square root of 9 times the square root of 5. So the square root of 9 is 3. And the square root of 5 can't be simplified any further. It's not divisible by anything from that list. Okay, and very quickly before we move on, let's say we had, let's look at the square root of 50. Right, so some people might automatically say, okay, 50 is 10 times 5. 50 is 10 times 5, but 10 is not a perfect square, and 5 is not a perfect square, and so you've just broken it up into 2 radicals that you can't simplify. So you always want to go back to this list. I don't care that it's divisible by 10 and 5. That doesn't help me simplify it at all. So looking at the list, I can see that it's divisible by 25. So I'm going to break it up into 25 times 2, and now the square root of 25 is 5. So the square root of 50 is 5 times the square root of 2. So don't just jump to any kind of factors that any 2 factors that multiply to it. You specifically want one of those factors to be a perfect square. Okay, so C is the square root of 300. So I can break that up into 100 times 3. So the square root of 100 is 10, and 3 does not have any perfect square factors, so the square root of 300 is 10 times the square root of 3. And then 35 is divisible by 7 and 5, so you can do 7 times 5, but 7's not a perfect square and 5 is not a perfect square, so that's not going to help me break it up. Those are the only factors besides 1 and 35, so the square root of 35 cannot be simplified. It's just going to be the square root of 35. Okay, for E and F, you'll want to look at your list of perfect cubes and perfect fourths. So on E, the cubed root of 54, so looking at my list of cube roots, I can see that it's divisible by 27. So I'm going to break that up into the cubed root of 27 times the cubed root of 2. So the cubed root of 27 is 3, and then I can't simplify the cubed root of 2, so it's just going to be 3 times the cubed root of 2, negative 3, sorry, because I have this negative in front. Okay, and for F, I'm looking for the fourth root of 243. So now, since I'm looking for the fourth root, I'm going to look through this list. Okay, and I can see that 81 times 3 is 243. So this is going to be the fourth root of 81 times the fourth root of 3. So the fourth root of 81 is 3, and then this one can't be simplified. That one stays under the radical. So notice the way that I always write it is I always write the first one that is a perfect square, cube, or fourth and will come out of the radical, and then my second one is always the one that stays under the radical. Example 5, simplify. Assume that all variables represent positive real numbers. So A, the square root of 25, p to the 7th. 25 is a perfect square, which is 5. And then p to the 7th, so the square root of that. So remember, I'm going to take 7 divided by 2 is 3, which means it's going to be p to the 3rd. And then I have 1 left over, my remainder 1, so it's just going to be p to the 1st inside the radical. Okay, and then b is the square root of 72y cubed x. So the square root of 72, I can break that up into 9 times 8, but 8 has a perfect square factor, so I'm going to try to think of a higher number. That's a perfect square. 36 times 2. So the square root of 36 is 6, so this is 6 root 2. So I have 36 and 2, and then for my y cubed, I can put squared and then the 1 left over, so 2 plus 1 is 3. I put this y squared here in the one with the perfect squares because it's going to come out of the square root with the 36. And then x, there's only 1, which means there's not enough to come out of the radical. So again, remember I always put my first radical on the left side. I always put it so that it's a perfect square and it'll come out of the radical. The one on the right side, I always put the one that's not a perfect square that's going to stay under the radical. So this one is going to be 6y, and then this one stays the same, 2xy. I'm just putting it in alphabetical order because I like that better, but it doesn't matter which order you put the variables in. Alright, for C, we're looking at the cubed root of negative 27, y to the 7th, x to the 5th, z to the 6th. So again, we're breaking it up into two parts. Remember, you're looking at cubed roots, so negative 27 is a perfect cubed. And then 7, y to the 7th, so 7 divided by 3. I can have, well, you're basically doing any multiples of 3. So the highest multiple of 3 is 6, and then 1's left over. And then for the x to the 5th, the highest multiple of 3 is 3, and there's 2 left over. And then z to the 6th, then there's no z's left over. So the cube root of negative 27 is negative 3, because negative 3 times negative 3 is 9, times negative 3 is negative 27. And then the cube root of y to the 6th, 6 divided by 3 is 2, so that's y squared. The cube root of x cubed is just x, and the cube root of z to the 6th is z squared. And then this one is just going to come straight down, the cube root of yx squared, or x squared y would have worked also. D is the fourth root of 32a to the 5th, b to the 7th. So again, I'm breaking this up so that I have any perfect fourths, and then the right side are the ones that are not perfect fourths. So 32 is 16 times 2, and remember you're looking at your list of perfect fourths. So 16 times 2, and then a to the 5th. Remember, for your variables you need multiples of the index, so I need multiples of 4, so this would be a to the 4th, and then there's one a left over to make 5, and then b to the 4th, and then there's 3 more left over to make the 7. So all of this side is going to come out of the radical because it's perfect fourths. So 2 times 2 is 4, times 2 is 8, times 2 is 16. So the fourth root of 16 is 2. And then the fourth root of a to the 4th is just a, and the fourth root of b to the 4th is just b. So negative 2ab times the fourth root of 2ab cubed. Okay, here's a rule that we're going to use to deal with radicals. So the kmth root of a to the kn is equal to the mth root of a to the n. So notice that my k's cancel, because what you're actually doing is you're taking that exponent kn, dividing it by km, so your k's cancel and you have your numerator is your exponent and your denominator is your root. Okay, so just a quick example with numbers would be if I had the 18th root of x to the 4th. So I could take 4 over 18, and that reduces to 2 over 9. So remember, my denominator is my index, so that would be the 9th root of x squared. Example 6. Simplify. Assume all variables represent positive real numbers. A is the 12th root of 2 to the 3rd. So I can take my exponent divided by my index, 3 over 12, is the same thing as 1/4. So that's going to be the fourth root of 2 to the first power, or just the fourth root of 2. And then b, I can take, again, my index divided by, my exponent divided by my index, 2 over 6, which is 1/3. So this is going to be the third root of t to the first. Okay, remember to multiply radicals using the product rule. We have to have the same index. Well, in this case, this is the square root of 5 and the cubed root of 4, so the indexes are different. So we can't use a product rule, but we can use exponents to be able to make them have the same index. So we're going to rewrite this with exponents. So remember, this is 5 to the first, and the square root is implied to have a 2. So this is going to be the same thing as 5 to the 1/2 times, again, if there's not an exponent, it's understood to be 1, so this is going to be 4 to the 1/3. So now we need to get a common denominator for the exponents for the fractions. So for 1/2 and 1/3, my common denominator would be 6. So 1/2 is 3/6, and 1/3 is 2/6. So this is going to be the same thing as 5 to the 3/6 times 4 to the 2/6. So the denominator is my index, so that's the 6th root of 5 cubed times the 6th root of 4 squared. Okay, so 5 cubed is 125, and 4 squared is 16. So now that the indexes are the same, the 6th root of 125 times the 6th root of 16, now I can use a product rule. Okay, so 125 times 16 is 2,000. So it's going to be the 6th root of 2,000. Okay, in our next examples, we'll be doing some application problems, and some of them will involve right triangles, and so we're going to use a Pythagorean theorem, which is a squared plus b squared equals c squared, and we use that when we're finding the missing side of a right triangle. Now, so if this is my right triangle, it doesn't matter which you label a and b, those can be switched. C is always this longest side, the hypotenuse, and it's always across from the right angle. So example 8 says find the length of the unknown side in each triangle. So I can label this a and b, and I'm looking for c. So a squared plus b squared equals c squared. So it's going to be 8 squared plus 14 squared. 8 squared is 64. 14 squared is 196. 260 equals c squared. And then we'll take the square root. So you're not done when you find c squared, you're done when you find c. So we have to take the square root, which would give me c equals the square root of 260. And then I can simplify that. So remember, I'm trying to find two numbers that multiply to give me 260, but one of those has to be a perfect square. So I think it's divisible by 4, so that would be 4 times 2 goes into 26, 6 times 25 times, so 4 times 65, and then 65 is 13 times 5, but none of those are perfect squares, so that's the most that I can simplify. Alright, so the square root of 4 is 2, so it's going to be 2 times the square root of 65. Alright, for example B, notice that they give us C, the hypotenuse is 6, and we're looking for B, so I'm still using a squared plus b squared equals c squared. So 4 is A, we're looking for B, 6 is C. So it's going to be 4 squared plus b squared equals 6 squared. So 4 squared is 16. 6 squared is 36. So I want to find b squared, so I'm going to get the b squared by itself. So subtract 16 from both sides, which gives me b squared equals 36 minus 16 is 20. And then remember, I want to know b, not b squared, so I'm going to take the square root of both sides, and then I can simplify the square root of 20. That's going to be 4 times 5, so that's 2 square roots of 5. The next type of problem we're going to be doing is using the distance formula. So this is when you're given two ordered pairs and you're asked to find the distance between those 2 points. So the formula is the square root of, to take your two x values and subtract them, and then square it, and then the difference of your y's squared and add those together. Okay, so example 9a, my ordered pairs are 2, -1, and 5, 3, and we're finding the distance between the pair of points. So my formula is x2 minus x1 squared plus y2 minus y1 squared, and then take the whole square root of that. So my x's, I have 5 minus 2 is 3 squared, plus, take my y's, 3 minus -1. So when I have minus and negative, that's adding them, so that's 4 squared. So that's 9 plus 16, which is the square root of 25, which is 5. B is the ordered pairs -3, 2, and 0, -4. So I'm going to take 0 minus -3 squared plus -4 minus 2 squared. So minus and negative is plus, so that's going to be 3 squared plus -4 minus 2 is -6 squared. So 3 squared is 9. -6 times -6 is 36. So 9 plus 36 is 45. And then the square root of 45, we can break it up into 9 times 5, and the square root of 9 is 3 times the square root of 5.